He is okay, just so everybody knows. Okay, yeah, and then this goes straight to lunch, and after that, the room is going to go open back up. We're going to go back to plant areas. So after this, just keep track of your stuff. All right, so first up is George Schuler of the Nature Conservancy. He serves as the Eastern New York Chapter's Director of Conservation Science and Practice, and he serves on a statewide team of freshwater experts, spearheading efforts to change state policies with respect to water management. He also works on fisheries management policy with the Atlantic States Marine Fisheries Commission and leads a small team of conservancy staff from across the North America region on the emerging continental approach to conserving these species. His presentation today will focus on science and policy development for in-stream flow. We all welcome George Schuler.
Great. Thank you. So I am probably going to, at some point, pull back the screen and show you the wizard when it comes to science informing policy, but hopefully I can distract you with a nice story before that. So just to kind of ground everybody, we all know that most of the Earth's surface is covered in water. The handy thing for me to always remember is that less than 1%, 1/2 of 1%, is actually fresh water that we can actually access that isn't tied up in snow or ice or in groundwater. And so that means we have a really small amount, even in water-rich areas, and it is all we will ever have, as Carl Sagan used to say. And the other thing to keep in mind is we talk about water. Water people have a problem. They talk about water as water instead of all the things that water touches and allows us to benefit from economically, ecologically, spiritually. And I think that kind of undermines the value of water. But this is just to show that water touches our lives with a lot of different ecosystem services, everything from aesthetics and spirituality to how much hydropower it can generate. And that pattern of water, not only where it is on the Earth's surface or in New York State, but the timing of it across the year is really important, and it drives nature and the patterns of nature we see. So this is a hydrograph. The light gray is kind of the natural part of a hydrograph, if you can imagine. The peaks on the far left are the April showers, which bring May flowers, and in the middle where it's low are the dog days of summer where there's not a lot of water. But the point here is that there is some space between a natural, unregulated river's flow and kind of those critical pieces in dark gray that are really necessary for ecosystem health or ecological maintenance. And that includes keeping river channels healthy so that they can flood, so that fish species can migrate. And so New York has this really interesting situation, being, as Jim Tierney and Scott Cuppett kind of teased us a few years ago, the Saudi Arabia of water, meaning we have a lot of it, in that we have really diverse ecosystems. We have 1,000 acres of square miles of lakes and ponds and 80,000 miles of rivers and streams. Everything from ponds and wetlands in the Adirondacks to the Great Hudson River, to headwater streams in the Catskills and elsewhere. This real diverse of biological diversity, of aquatic diversity, unlike a lot of other states, in fact. We also have this tremendous dependence on it from our own human perspective. There are roughly 20 million New Yorkers. You would be amazed at how many of them drink water, or use water, or have water in their basements. And a great deal of them live in urban areas. And I'm not going to have it, but there's a report that the Conservancy did globally of over 500 cities, looking at those cities and where source water protection from a conservation standpoint could actually benefit their water supplies. And it highlighted 6 or 7 New York cities: Syracuse, Binghamton, Buffalo, and of course New York City. But so water is really fundamental to who we are ecologically and who we are from a human standpoint. And this map shows you, and it's hard to read from the back of the room, but it shows you this is all of the permitted water withdrawals in New York State, all of those that are 100,000 gallons or more a day. And the color coding is by industry or sector. We can see an enormous amount of those are pink in public water supply. If you take New York City out, it drops down from the biggest use to the second or third. But water supply, creating power, industrial uses, and agriculture and irrigation, over 300,000 acres of irrigated lands in New York. So we depend on water in New York, not only for our vast treasure trove of biodiversity, but for our economic and social well-being in a really profound way. And most of those power plants are actually thermoelectric power plants, so this is cooling water and has a very different impact than the water that goes into beer at Omegang and other industrial processes. The water supplies for New York City and other communities have different impacts. And the thing that I thought was really interesting is we know that agriculture is moving from the West and Midwest into the Northeast as a result of some economic drivers in the US and climate change. But this is from one of the last USDA reports. The actual land amount in agriculture in New York State is increasing, meaning not that we'll use more water necessarily, but that pattern of use will shift. The times that we need it, the places that we need it, and what happens to it when it runs off the landscape will change. So 3.5 billion is the amount of direct economic impact from New York's portion of the Delaware River, to drill in for those of you from municipalities. So water, not just water sitting there or water for water supply, is really critical. In New York, it directly touches over 32,000 jobs. This is the Delaware Bay or the Delaware River portion of New York. So a small piece of a river basin, and enormous economic and social impact. These are things like people who work at sewage treatment plants, recreational fishing guides, anybody who is connected to a water body. Multiply that times all the large basins that we have across New York State, and you begin to see our future is intertwined with water. And it's a really uncertain future. I hear every day about the droughts in California, and could that happen here? And what I try to remind people is that it's not just a lack of rain and snow. It is climate mixed with economic development, mixed with social trends, mixed with some environmental concerns, and presto, you have a crisis on hand. So we're not there, but the conditions that circulated are not kind of alien to us. The green on this map are where different industries are settling. So this is kind of the best image that I could find about our economic development pattern in New York. And economic development is something that's necessary for communities, it's necessary for the state. New York is open for business. The question really is, how do we balance this and the water needs that fuel this with the water needs of future businesses, future nature, future people? And I was looking this up. This is the Drought Watch map from May of this year, and it highlights, it was used in the New York Times articles about the California drought. The interesting thing I found out when I went to the Northeast was, and my garden suffered this, the amount of dryness that was in the Northeast this year. And Beacon, New York, where I live, is in, I think, phase 2 drought warning watch, whatever they're calling it. But the fact that these shortages do happen, and if they happen at the wrong time, that creates a problem. But this is an uncertainty around climate change and weather patterns in general. And when you have that, when you have economic development, the uncertainty of what the planet and Mother Nature are going to do, you get conflicts like this. How do we make choices? This is a sign from Kingston, New York, and the Niagara bottling facility issue. How do you begin to make choices that meet collective needs over the long term when you don't see them coming, whether it's climate change or economic development or social trends in using water? So this is where science comes in, and it's a great time to be alive in terms of science. There is more science and more data about water resources and how we use water resources than you can shake a stick at. The challenge of it is that it's decentralized and it's really complex. And scientists like myself say, oh, but wait, we'll have something better if you give us another year or 2 or 5. But there's a tremendous amount of information. And so one is the Conservancy, and I'm going to highlight Conservancy examples because that's what I'm familiar with. The Conservancy has worked in the Delaware, Susquehanna, and Great Lakes Basin and expanded it statewide to come up with ecological flow requirements. So essentially, it answering the question, how much water does a river need at different times a year? So you could start to look at impacts to aquatic ecosystems from water withdrawals or water usage or water quality impacts. We, working with USGS and NYSERDA, have developed a new tool that can help define stream flows and look at cumulative impact of water withdrawals. For any point in New York State, and it's a free and public tool, it's on the USGS website. You can delineate your watershed, just put where you're concerned about on the map. It pulls together a bunch of parameters that are really important to informing stream flows and gives you results that are useful to regulatory agencies and municipalities like the 7Q10 or the 7Q2 in terms of water quality dilution.
What's the reference here?
If you look at the stream flow estimator tool on USGS website, you'll find the downloadable program. And it uses StreamStat, so it uses national data. And then it kicks out, and this is why I say it's never been a better time to be alive as a scientist or have science for water. We have lots of it. But the problem is, and I get requests from communities all the time, can you send me that link? But the problem is that it kicks out really gorgeous spreadsheets like this that enable you to do all sorts of stuff, and that's complicated. But the spreadsheet that gets kicked out of the Streamflow Estimator tool allows you to start putting in withdrawals and seeing what the cumulative impact to that point in the river is. So you can visually see whether if your critical threshold is that red line, and the green line is what you computed after you put in that new bottling facility or that housing development, you know you have a problem, and you have the statistics to show it. So something we couldn't do 2 years ago very easily can now be done relatively simply at the press of a button. The USGS and the Conservancy have also developed a spreadsheet that kind of gives you, and albeit complicated, but dashboard for how the different environmental parameters are impacted by water use. And so green is good, green is fine, yellow is starting to be a warning sign, red is you're kind of in a danger zone, and black, you're kind of in trouble. And these look at the parameters that are part of the Conservancy's ecological flow recommendations for 2 states. But it starts to distill something that was really complex math into something that begins to approach a dashboard that you can see what the environmental impacts are to your rivers and streams that you're dealing with. And more recently, the Conservancy, so that kind of frames, and academics at Cornell and other places have really been good at this as well, defining the environmental needs of a river, and that science is out there. The other piece is how much water do people need? And this is where we get to a little bit fuzzier zone, because rarely in these discussions about flow recommendations do users get asked. So the Conservancy and Columbia University and World Wildlife Fund started to put together a risk assessment for New York's water withdrawals. And you could look at it in terms of these points, which are the water withdrawals, or through watersheds. But just to kind of get your eyes oriented, the more orange it is, that means the higher risk it is, but also higher risk in terms of water quality and water quantity. Black dots or gray dots are simply water quantity risks. And the more yellow it is means it's purely water quality risks. And the risks here are things not just like, are you going to run out of water, but it's what is your exposure during the driest time of year if you're a water bottling facility? What is your exposure to flood risk during the peak flood years out of a decade? And so it begins to give you a screening tool as both a community and a water user to understand, wow, what do we have to be concerned about here in terms of our water use, even if there's plenty of water in that stream or in that reservoir from our eyesight. Oops. And lastly, we can use things like the Forest Service's ability to provide clean water analysis to begin to show what are the watersheds in the state that we should focus on protecting, which are blue, source water protection, or orange or red, which are the ones that are really degraded from, they have potential for sediment runoff, they have lots of roads, they have people living in them. So, and what do we do in those areas that we can target? And so you might ask, how does all of this science, which is locked away in NGOs, some of the state agencies, USGS and others, and academics, how does it inform state policy? And this is where I'm going to pull back the curtain a little bit, and maybe many of you live behind the curtain with me, so this won't be a surprise. But science doesn't give you the answer to how much water you want in your rivers, or streams, or reservoirs, or groundwater aquifers. That's a social question. And so what I can tell you about how this informs policy, and Jim Tierney's not in the room, and he would be able to explain this better, but so I took a hydrograph and I kind of cut it off. So spring is on the left and it gets towards summer on the right. The colored lines in the middle are actually what we call a pass-by flow. And they are kind of different versions of what the state may come out with any day now. But my point is that, so it's a pass-by flow, meaning you need to leave as much water as underneath it going by your pipe if you're taking something out of a river. It does a really good job of protecting the low flow times of year. But it leaves everything else on the hydrograph kind of up for grabs. And so what I would say is, this is one measure of protecting our in-stream flow, and it's the one thing that science has articulated, that low flow times a year are really sensitive to aquatic biodiversity, but also to water users. But we haven't dealt with what happens to the rest of the water in the river, or in the wetland, or in the reservoir, the other times of year. So this is our societal agreement right now based on the science we have. We've not had the discussion or applied the tools for how do we manage the rest of the water. This is kind of managing to the bottom. And so this came up, I think, earlier today and yesterday during the panelist conference call. There's a real need for communities, water users, and other stakeholders to begin taking information like this, and there's a task that's on my shoulders and other scientists, but taking information like this and really starting to use it for how you think about the future of your communities, your industry, your nonprofit's mission. We can start taking that complex spreadsheet data and creating maps and interactive tools and even games that allow communities. So what you're looking at is a watershed in the Hudson River. The colored dots are different types of industries. Their size denotes how much water they withdraw in the white around that. And then the colored dot is how much they consume. And what you probably can't see is this little equation up here. So in this watershed, small watershed, almost 23 million gallons a day, something like that, I can't see, are withdrawn, and 1,600 are actually consumed. They're used in a way that doesn't go back into the river. So this watershed, even though it has quite a bit of development, it may have some timing and release issues of water use, and water risk is incorporated in this, but I won't talk about that right now. There's probably some room to have discussions about economic development and using water and water for conservation. The challenging situation is when you get into a comparable watershed, a very different mix of water use, a lot more agriculture and mining and extraction. And if you look at how much water is withdrawn, it's 10% of what that previous watershed was. But its consumption is almost the same. And if you look at the fraction of the two, a lot of industries are actually taking water that isn't being released right back into the system. It's not good or bad, but the data shows you that you're living in a different context and you have different choices to make about land use, economic development, water conservation, water resource planning. And it's putting information in kind of a slightly more easy to digest chunks like this that could benefit local decisions and state policy. But I think the game really is going forward in local decisions. And so one of the things the Conservancy is working on is trying to figure out how to turn really complicated spreadsheets and Excel databases and GIS maps into something that's a little more planning friendly, not only for municipalities, but for water users. And so we've engaged NYU to help with this, as well as Deltares, which is the Dutch National Water Institute, which has done a lot with gaming and decision making around water resources for communities and stakeholders. But that changing the data and the information that's available is on us. The galvanizing it into policy change is on all of us. Any questions? Ryan, I don't know if I went over or ran.
George, last slide. So what's, you want to take all that spreadsheet and GIS stuff and make it testable or easily digestible?
Yeah, so there's two levels to this. One level for the engineers, and probably Jay, you would be fine with the spreadsheet and kind of the software that we've developed. Those tools speak kind of in your language. The question for us really is, how do we put it in the language of someone like, is Mary McNamara in the room? I'm not going to pick on her. But she's the one who often calls me with stuff around the Esopus. And Mary's a really bright person. But the spreadsheets and the models and the GIS stuff doesn't speak to answering her questions. So how do we turn this into something that answers the questions of local needs? Whether you're an engineer, or whether you are a concerned citizen, or whether you're Bob who runs the tubing business on some river. And that's really the challenge. And it's a really different approach to conveying data and information. Andrew.
George, so some of these issues are definitely dealt with at a state level, but do you have examples of municipalities or perhaps future municipal groups that have dealt with taking this information and then run with it?
I don't. I think that's one of the things that we'd like to learn. Who has done this across the state, if not in the state, in neighboring states, and what's worked for them? Because I still come up with, I end up making maps that make sense to me, or data sets that make sense to me, but it may not make sense to the folks in Rockland County or up on West Canada Creek. So I think that there's a real dialogue that needs to happen with and finding those examples around the state. Laura?
So I was kind of thinking on the same lines, but from a different angle. I was just curious at what point in decision making, or what level of decision making you feel like thinking about ecological flows and nutrient flows become, you know what I mean? Because not everybody addresses obviously every level of consideration. So is it something we should be thinking about proactively? Or like, what are you doing with that answer?
Yeah, I think it is. I think especially the environmental needs get to, well, I'm from the Nature Conservancy, so the environmental needs need to get put front and center at the very beginning and being proactive about it. But I also think the other water user needs and future needs, and I'll give you an example. So is anyone here from Kingston, or going to talk about the Kingston example? So my understanding about Kingston was that Cooper Lake could provide 6 million gallons a day, and Kingston and Ulster County used 4 million gallons a day, and the bottling facility was proposing 1.75 million gallons a day, which doesn't leave you a lot to plan around if there's a drought or some great new economic opportunity comes in or something else. So I think that planning proactively for water in general and using as many of the values we can kind of harness and put into that calculation is something we need to do now.
So the level of the process is through, so if you like Jordan was saying, comprehensive planning, to be able to just...
Yeah.
Okay.
That's what I would suggest.
Maybe you're assuming this, but it doesn't tell me that it's been integrated. It isn't just how much water or how clean the water is. It's like, what is that gray area of the extra
Yeah.
water? What is it actually doing? I think you need to know in a qualitative way. Is it nourishing some grand set of bug turtle
Yeah.
habitats, or is it in an issue with farmers, or is it? You need to connect those variables to what's going on, really.
Yes, yes. And so for,
Rather than just think of the as flow charts on a computer.
and that's exactly the issue. So that most of the environmental stuff we've done has that embedded in it. I'll be honest, when we have done environmental flows projects, the human part, who's using what and how they value it, hasn't been added as well as I would like it. But doing that and then conveying it to people so that they can see it is a real challenge.
Well, I actually think it's great. And what you're listening to, what's bringing to mind is, like, we're about 8 inches down of precipitation in 2015. And when you listen to weather forecasters on TV, they just sort of started mentioning that outside of their mouth. And so all summer, as there was another wonderful sunny day for people to go to the beach, what most people are exposed to about the hydrologic system is, oh, I'm not getting rained on today, it's a good day.
Yeah.
And because a lot of people do have, water infrastructure, most people, their taps don't run dry. And in many cases, they can still water their lawns because there has been such a great effort of preserving the New York resources. And so there is this huge disconnect between the water users, the water rate payers, the voters,
Yeah.
and what's really going on because of the expected climate change in New York, there's going to be maybe around the same amount of annual rainfall, but it's going to be usually different. So the reservoirs are going to get filled most likely. However, the natural systems are going to be hurting. There's going to be the microbursts and
Yeah.
mini droughts. And I think it's really vital what you're doing is really trying to connect all of those things together so people can be more informed and they can sort of be better, water-wise citizens.
One of the things that came up in our panelist discussion yesterday on the phone, I think it was either Scott Cup or Simon, said there's a real fundamental lack of understanding where our water comes from, because you see the tap go on and you see the sunny days, but you don't put all the pieces together. And that's a really key educational opportunity and challenge that we have.
Regarding information technology, and the maps that we had of the watershed, there was the available water and what the water is being used for. Has there been consideration of drilling down where you click on that map and you get the data for a particular subsection of the watershed, or we can look at that data?
Yeah, we've thought about doing that. So we don't have a website up that does any of that right now, but we're planning in the next year to develop that so that you can drill down at least to a certain extent and get sub-data or be directed to where you can get that data.
You reference like a GIS filter, or you something like that, so you can then drill down?
Yeah, except that it won't require, it'll be more like a web map service that allows you to access that data. And some of it, I think, will be canned outputs so that people that aren't technical can see it, but there'll be links for people who want the actual, a spreadsheet of data or a shapefile or something to use.
Do you have examples of businesses? You brought up the Kingston example. Do you have examples of businesses or know of groups that are organizing businesses to think about this proactively in the way that you'd like to shout from rooftops that other businesses are thinking this way?
Not in New York. And it may not be that there aren't any, it's just I'm not aware of them. But one of the things the Conservancy and some of our partners would like to do over the next few years is actually start partnering with them, either tell their story or to create those examples. So if anybody knows of an industry that is eager to work on this issue or is working on this issue and would like a little light on their efforts or some support or something, that would be really great to know.
Well, I don't know how well the brewery business is behaving, but I do know that there was a group that was a group like microbreweries against fracking.
Yeah.
So they did take an organized stand to try to, help protect water.
That's great. You, and then you.
Yeah, you made a statement before, and I wonder whether you can expand on the environmental and social implications so that I understand better. You mentioned that some systems will take water but not use it.
So thermoelectric plants or power plants are a really good example. They take in water for, this is not to say there's no impact, but from a water use standpoint, thermal plants take it in, cool off their, make steam, cool off their equipment, and put it back. So that water is relatively, it's back out in the world. You could use it again. Somebody could take it. Other industries, and let's say agriculture, feeding livestock, a cow drinks water. Even if the cow processes the water, it takes a while for it to work its way back into the stream or as rainfall. And so it's kind of out of the loop until it shows back up on Earth. So there's a difference between withdrawing water, taking it into your facility or your community, and consuming water, which means that it's not going to be available for immediate reuse.
So you weren't specifically talking about water utilities, you were talking about these other uses.
Yeah, I was talking about any use that kind of takes it out of the system and makes it unavailable right away. Because it means that should a drought come, that water it was there yesterday, but it's not available today. And so it's not that it's bad, it's just that there's a set of choices that go with that. Understanding how much of that is happening in your watershed or your community is a useful piece of planning information.
Maybe preaching to the choir on this, but I've been involved with environmental concerns, specifically with water quality, for over 25 years. And one of the things that I've noticed is the use of technology exponentially expanding what we can do, what we can understand, what we can interpret. Like, I look at your pictures, I look around the room, and I don't see college-age people here. I don't see high school kids talking about starting their own businesses, being entrepreneurs, and how they integrate, or we know clearly how we're going to reach those people and get them to think that that's our future, not us.
I think it's a really good question, and I think that there's a lot of work to be done, both getting high school kids, but I think, that we could have hackathons around water issues or programming apps. We could also, this idea of sustainability, if we can encourage the Hudson Valley as a sustainability incubator and have people starting businesses around water-related things and fostering that would be another piece of the puzzle for us. But I agree with you. I think there's a real challenge there, but it also presents an opportunity.
Thank you.
Thank you, George. That's good stuff, I have to say. It's great to see TNC doing this work, and just coming from somebody who works a lot with, the youth and the public, that data interpretation piece and making it fun, and like the last commenter said, getting the information out there is critical. It really is. So moving on, just so everybody knows, we're going to end this session at 12:15, start lunch a little early because Al Appleton is here now, so we're going to try to squeeze him in after lunch. So next up is Cliff Callanan. He's a professional engineer who grew up in the Finger Lakes region, and he works with the New York State DEC for more than 25 years on a wide range of water quality and water quantity projects. He is presenting today on how nutrient enrichment can impact potable water supplies in lakes and reservoirs, and how New York State is developing numeric nutrient criteria thresholds in order to protect these water supplies.
morning, all. Thanks for coming out today. Thanks, Ryan, for that introduction, and thanks to Scott, Maureen, and Simon for pulling all this together. Just quick clarification, if I can. What time do I have to run to, given that last qualifier? Okay, that's good. Okay, good. Okay, so I thought I'd start with a quick trivia question, just to get things rolling here. How many people here can identify that body of water and the defining event that sort of put that on the map as a poster child for nutrient enrichment and drinking water issues? Okay, so what's that body of water, Scott? Lake Erie, correct. So let me get oriented here. So that's Lake Erie, and the event that sort of put it in prominence, I think Chai-Ho jumped the gun on this for me this morning, which was the Toledo Public Water Supply Do Not Drink event last year, early August, that put a do not drink, do not use water advisory for 400,000 people from Toledo. To me, the daunting thing is, if you look at the panel in the left here, it's not just Toledo that uses the western basin of Lake Erie for drinking water supply. That's a USGS slide showing all of the water intakes for the western basin of Lake Erie. And just for perspective here, Lake Erie is about 50 miles across. So you can see the footprint of that bloom. You'd be hard-pressed to get a water intake pipe outside of that footprint of that bloom, particularly here, where the bloom is virtually contiguous across Lake Erie. Okay, so quick bio. Grew up in the Finger Lakes. Ryan covered most of that. My education is from Cornell, and I'm a professional engineer. I'll repeat the contact information, and there are some cards back on the table. So, quick overview of the talk I'm going to try to give you folks today. It may be a bit truncated given time limits, but what I'm really trying to convey here is why the concern with nutrients and drinking water. In a moment here, you'll see how many different contaminants can come into play for drinking water, either directly or indirectly related to cultural eutrophication or nutrient enrichment. A proposed solution, a multi-barrier approach. You've already heard some mention of that a couple of times already today. Basically, source water protection coupled with treatment. And our approach, which is proposed numeric nutrient criteria. And then I'll talk a little bit about Orange County perspective, some data the department has collected for some of the water supplies in Orange County. And the learning objectives, again, sort of go side by side with some of these elements of the presentation outline. Okay, so to me, this is the most important slide of the presentation. And I put this together for a talk at Albany Medical College several years ago. But really what we're talking about is human health protection. And there are a series of contaminants that can sort of be exacerbated by nutrient enrichment of drinking water supplies. So the first class are something called disinfection byproducts, which form when you take natural organic matter that originates in either on the landscape and flows to the lake or river, or develop right in the water body itself through algal production, or as Chai-Ho clarified, cyanobacteria growth. So disinfection byproducts are associated with cancer of the colon and liver, basically the digestive tract, as well as bladder and kidney. It also has acute reproductive effects, birth defects, stillbirths, that sort of thing. So the second class, or the second contaminant of concern, and again, this is an indirect association. We'll talk about how this comes about in a moment, but arsenic can become enriched in the water column as a result of some of the processes, the ecological processes that sort of are kicked into high gear by nutrient enrichment. And arsenic has a strong association with cancer of the bladder, kidney, as well as liver, prostate, and lung. So you begin to see here, too, the potential for an additive or a synergistic effect targeting similar organs or organ systems. And then the last group that has been in the news quite a bit of late are these cyanotoxins that are produced by cyanobacteria. They're more well known for their acute toxicity, either liver toxins or nervous system toxins, but there is also some evolving linkages to carcinogenicity and also some neurological disorders. Okay, so the second sort of learning objective here is sort of how does this all unfold? I mean, that's quite a suite of contaminants that I'm proffering is connected back to nutrient enrichment. So the first step is nutrients, and again, I'm going to leave some of the discussion on this slide out, largely that brown box in the lower left corner. And we're going to focus on the nutrient enrichment, phosphorus being prime as the limiting nutrient for algae and cyanobacteria growth. So the watershed brings in phosphorus from various sources, sewage treatment plants, agriculture, stormwater runoff, septic systems. That increase in phosphorus triggers an increase in algal growth or cyanobacteria growth. That algae and cyanobacteria, coupled with the terrestrial material coming off the watershed, contribute to this central box here, natural organic matter. So natural organic matter in and of itself is not toxic, let's put it that way. It does pose some problems for drinking water supplies for other reasons, but it's actually when that material gets dosed with a disinfectant, a strong oxidant, that we end up forming those DBPs. And then as that natural organic material settles down through the water column, it consumes oxygen at the bottom of the water column, okay? And that consumption of oxygen leads to reducing conditions in those bottom waters, which can allow phosphorus to come up out of the sediments, and also things like arsenic, which is strongly redox sensitive, is the chemical term for it, that when you reach reducing conditions or anoxic conditions, arsenic basically decouples from sediment particles and can re-enter the water column. So this is basically the ecological side of the picture. And then the drinking water side is over on the right-hand panel. This is a slide developed by a colleague of mine who is another principal investigator from Department of Health, Jim Hyde. So again, what we're talking about here is cyanobacteria produce cyanotoxins, which are drawn into the treatment plant. Natural organic matter treated with an oxidant, a disinfectant, which is essential. Maureen touched on this earlier with her wellhead and cholera epidemic in London. You really have to disinfect water. In fact, as the EPA official talked about this morning, the FAD, which is filtration avoidance determination, means you don't have to filter, but you still have to disinfect. So the point here is once you dose this natural organic matter with a strong oxidant, you can produce these disinfection byproducts. And then arsenic, again, is taken through the pipe, brought into the treatment plant. Some of these are removed by treatment, but it's becoming increasingly difficult to sort of stay ahead of that curve. Okay, so this is a more sort of artistic version of what we just talked about. I've left a copy of this. Don't think of this as homework per se, but we're covering a lot of ground here. It's sort of a quick synopsis with steps around the base of the lake there. It's back on the table I'm sitting at, which has a coffee mug and so forth. Please feel free to take a copy of it, as well as a card back there. I prefer you didn't try to read through this while I'm talking, but feel free to take a copy. It's a lot to cover. Okay, so our proposed solution really draws on elements of the multi-barrier approach. So multi-barrier approach has been touched on already today. I think there's actually going to be a whole discussion of this later on by the Department of Health. This is a picture from a Canadian source. It basically breaks out into two main components, which is source water protection. Think of it as this upper panel, which is preventing contaminants from reaching the source water, the lake, river, groundwater, what have you. And the second main component is water treatment. Our focus will be on source water protection. And then there are policy elements to this as well, actually policy elements drawing from both the Safe Drinking Water side of things and the Clean Water Act side of things. The Clean Water Act primarily concerned with source water, controls, protection. Safe Drinking Water Act more end of pipe, making sure that contaminants are not reaching your faucet, your drinking water. Then there are monitoring pieces, again, raw water monitoring pieces, again, connected to the Clean Water Act, and finished water monitoring requirements under the Safe Drinking Water Act. And the key point here of a multi-barrier approach is a redundancy axiom. You want to have multiple layers in place to sort of prevent contamination from getting to, to the public, basically public protection. Okay, so before I do an extraordinarily abbreviated version, usually when I do this talk, it's to scientific conferences, it usually takes about an hour and a half. So I'm really going to just show you the end point of our studies. But here are the participants in the study that I'm going to talk to you about that were instrumental in the process. Department of Health, one of the PIs was from Department of Health, Upstate Freshwater Institute, SUNY ESF, US EPA sponsored two studies that sort of funded our process here. It was done under the umbrella of US EPA's effort for the states to develop what are termed numeric nutrient criteria, basically establishing thresholds that would be protective of whatever use we are talking about. In this case, we're talking about drinking water. Okay, so just to take a quick step back, I like to throw this slide in just because, and it gets at the title of the session here, which is Science Informing Policy. So basically, scientists approach things through the scientific method, a portion of which is displayed up here. You observe natural phenomena. So things like observing that algae growth or algae blooms can produce cyanobacteria, can produce cyanotoxins, natural organic matter can produce DBPs, and then you basically go through a series of steps to formulate a hypothesis of how this is going on. You test the hypothesis. If it's valid, you take one course of action. If it's not valid, you go back. So basically, we set this process in place to try to establish criteria that we thought was protective of drinking water sources. So the next step, and a critical step in a scientific process, is to try to publish the material in refereed or peer-reviewed journals. Okay, we've done that. In a moment, I'll show you the results of that. Okay, so really cutting to the chase here, what we determined by basically looking at that relationship between nutrients, algal growth, natural organic matter, and those suite of toxins that could show up was that, and note this is job protection. These are proposed criteria. They're not on the books right now, but that's what I'm talking about today. And what I'll ask you to focus on, although in a minute we'll juxtapose these to other studies, is the chlorophyll A number. Chlorophyll A is the primary plant pigment found in algae, cyanobacteria, trees, etc. So we use that as a metric to estimate the mass of algae or cyanobacteria in the water. So what we arrive at is a mean chlorophyll threshold of 4 to 6 micrograms per liter, which relates back to total phosphorus being the limited nutrient of 12 to 17. So the next step, the final step in scientific method is to basically establish a theory, and the lay public get confused with the term theory. Theory is something that's quite well established by many different studies. Most people use theory really talking about hypothesis. But basically here you want independent study by others in the field, and that their conclusions should sync up with yours. So what I'm showing you here are a series of studies by others that arrived at drinking water protection criteria based on total phosphorus, the causative agent here. OECD is the Organization for Economic Cooperation and Development. It's an international body. And they came up with a recommendation of 10, which is somewhat lower than what we arrived at in our study. And that was published all the way back in 1982. British Columbia, drawing on similar information, but I think looking at it separately, also arrived at a total phosphorus level of 10. New York City Reservoir west of Hudson, TMDL, arrived at a total phosphorus target of 15 for the terminal reservoirs, the reservoirs that are directly used for drinking water supply. They also actually have a number, most people don't realize it, on the books for chlorophyll. It's a 7, but most people don't realize that sits there. So switching to the far right panel, and the piece that I think is more appropriate to focus on, simply because if you don't grow out the algae and the cyanobacteria, that litany of contaminant problems doesn't show up. So there are several studies here. 1989, this is in the peer-reviewed literature as well. Aruda and Fromm came up with a chlorophyll level of 5. And then this is the one I prefer to focus on here, is Colorado Department of Public Health and the Environment. They are basically the equivalent of the New York State DEC, which I worked for, Department of Environmental Conservation, and Colorado's Department of Health combined together. These folks came to me. I did a national webinar on this stuff half a dozen years ago. They saw it, they came to me, they asked for advice on setting up their own study. They went ahead and did their study from 2009 to 2011. They actually put their number, chlorophyll levels of 5, is actually on their books. They're actually using it for regulatory purposes. And just, actually I think next month, their peer-reviewed publication is coming out in the Journal of American Water Works Association. So that's available online. Okay, so just another quick side here, separate from the discussion of setting the criteria, is talking about cyanobacteria and growth factors that sort of determine whether cyanobacteria, that problematic issue for Lake Erie, will sort of come to prominence. So nutrients is a driver. As nutrient levels go up, cyanobacteria growth increases. Rainfall, and some of these are directly related back to nutrients. As rainfall increases, you drive more nutrients off the landscape into the surface water supply. That increases cyanobacteria growth. Wind and water agitation actually works the other way. Wind and moving water are less prone to grow out cyanobacteria. So rivers a little less prone, although there's a very prominent example. The Ohio River, I think a 600-mile stretch of the Ohio River had an enormous cyanobacteria bloom just this past year. Sort of thrown scientists for a loop, quite frankly. Temperature and seasonality. As temperatures increase, cyanobacteria have a growth advantage, and weather extremes. Okay, but the take-home message here is there's only one thing that humankind can really get their hands on around from a management standpoint, and that's the nutrient load. I'm going to skip right through here. This is national interest in the studies we've been doing. A series of publications. Again, if you touch base with me later, I can talk to you about some of these. This is the peer-reviewed journal. That's the foundation of what we worked on. This is a preview of the Colorado study. This is a JAWA, Journal of American Water Works Association, very good write-up based on the 40th anniversary of the Safe Drinking Water Act, talking about source water protection. And then this is a source water collaborative document that has a lot of really good material that sort of builds out the source water protection side. Okay, so Orange County perspective. I'm blowing through this stuff because I think I'm running out of time here. So we looked at 3 lakes in Orange County that are part of our normal sort of rotation to study water quality in the state. Yep, I'm sorry. You can see them listed up here. Lake Washington, Browns Pond, which I think is also called Silver Stream Reservoir, and Chadwick Lake. You can see aligned here the chlorophyll levels, which is where your eyes should focus. Lake Washington is in pretty good shape. It's a little above the thresholds that we're talking about. But Browns Pond and Chadwick Lake are well above it. So those are compromised sources from our perspective. Okay, and then I'd like to highlight a regional effort done on the Quissaic Creek, which has, I think, some very important take-home messages for those 3 water bodies in Orange County. Chadwick Lake, the print here, I'm sure you guys can't read, but experiences elevated levels of algal growth and water quality impairment during the growing season. That's consistent with our findings on water chemistry. Washington Lake, they're basically talking about protection efforts. They're understanding that it appears that it's in pretty good shape. This is the primary source of water supply for the city of Newburgh. And Upper Silver Stream, I think that's Silver Stream Reservoir, again, problems with algae levels. Okay, so contact information, and this little bar over here is that Ohio River bloom. And the orange is the extent of that cyanobacteria bloom, and millions of people's drinking water sources fall in there. So this is a panel on a webinar that I and colleagues from Colorado did for American Water Works Association. So, do we have time for questions, folks? Okay. Questions, folks? Okay, please feel free to catch up with me afterwards if you have questions.
All right, thank you, Cliff. Moving right along, next presenter is Dr. Jillian Decker. Jillian is an assistant professor of biology at Rockland Community College. Her research interests include nutrient impacts on phytoplankton, community structure, and ecological function, and the role of biogeochemistry of algal life history stages in large rivers. Her presentation will focus on biological organisms, specifically algae, as an indicator of water quality. Jillian.
Can everyone hear me okay? All right. Thank you for having me today, and thank you all for being here. I should also note that I'm also a member of the newly formed Wallkill River Watershed Alliance. So, shout out to that. Okay, so we are aware of the increasing numbers of human impacts to our water systems. Today we've heard a lot about nutrient inputs. Fecal contamination is another major human impact. Structures such as dams, and all of the impervious surfaces that we find particularly in more urbanized areas. In addition to that, many locations have removed natural buffers to the rivers. And there are a number of measures that you can use for identifying differences in water quality. There's a number of physical and chemical. Some of these include temperature, turbidity, things like Secchi depth. Chemical indicators include things like dissolved oxygen, nitrogen and phosphorus are two main plant nutrients, conductivity and pH. And these all tell you something that's a little bit different. What we can also look to use to tell us some information about water quality and what's happening in the water is algae as bioindicators, may be less known. So that's what I'm here to talk about today. Okay, diversity tells you a lot about water quality because it lets you know roughly if an area is heavily impacted or not impacted. You can also look at species indices. These indices are created and used very similarly to macroinvertebrate indices, which, like I said, are usually more commonly, people are usually more aware of and use more commonly. You can also look at species ecology by looking at and understanding the various tolerances and sensitivities of the species that you're finding in the water column. So sometimes you can tell a lot about what's going on in the water by simply looking at a specific species. Maybe one species will tell you about the acidity, or can tell you if there's high nitrogen, low nitrogen, high phosphorus. So these are things that you can find out without actually going out and looking and testing with a meter. You can just look at the species, and I could probably tell you if this species was collected, if this sample was collected summer, spring, winter, basic flow conditions, water depth. So all these things you can find out just by looking at what species are in the water column. And that's all based on species ecology. Another way that you can use algae is by using multivariate analysis. And I'll show you an example of that in just a minute. But before I move on, I want to talk about species indices for just a second. There are a lot of indexes out there using algae. Some of them use specifically diatoms, others use a more greater variety of algae. And what is great about the fact that there are a lot of them is that each one each one has been developed based on very specific areas. And the reason why that's important is what Dr. Sham said earlier, is no water source really is the same. So you have to go out, you have to see what's in the water, you have to see what's affecting the species in that specific water body, and then you have to relate it back to the various indices of water quality. Okay. And there's so many that I could talk about, but I decided to talk about one. It's the trophic diatom index. And there was an interesting study done in Europe using this index, and what they did was they took lots of samples above and below a wastewater treatment plant. And what they found out was that the river was already heavily impacted by nutrients. So the index by itself did not really tell them very much about how the wastewater treatment plant was affecting the river. What they did, interestingly enough, was they added a little supplement to that index. And they included something called the proportion, or looking at the proportion of the sample of species that were tolerant to organic pollution specifically. And when they added that small little supplement or that additional component, what they realized was that that component increased as you went downstream of the wastewater treatment plant. So the importance of this study and looking at that is that rather than put resources and energy into tertiary treatment for nutrients like phosphorus, they now indicated that, well, the plant itself isn't really the source of phosphorus. Phosphorus is already in the water. It's coming from upstream. Why spend the money, the time, the manpower to actually try to remove that when that's already something that's in the river? So what they were able to do is identify specifically what the wastewater plant and how that was affecting it by simply looking at species, okay, and understanding the ecology. Okay, so what I have up here, just to show you a couple of pictures. So when I talk about algal biomass, I have a filter here. That is a filter from the upper Mississippi River, actually. And you see it's quite green. And so that's one measure that you can use for biomass, that's chlorophyll. And then on the right side here is an inverted microscope, and this is what you would ideally use to go and identify all the different species in the water. Okay, so how can algae be used? What this graph is showing, so this study was done on the upper Mississippi River, and it was done in a collaboration between Fordham University and the USGS out in La Crosse, Wisconsin. And what we did was we wanted to see the different types of algae over the course of seasons, so spring and summer, and at different locations. The different locations are going to affect the species because of the fact that they have difference in flow, different competitive plant species, different depth, and all of that will also add into the difference in nutrient dynamics. Okay, so on the y-axis we see the relative abundance of the general algal groups. And you'll notice that I include Cyanobacteria under this umbrella of algae in this purpose because of the fact that they are photosynthetic, they are naturally competing with the rest of the algae in the water column. So one thing that you can see is that there's a big difference between spring and summer. So we see that water quality in the summer is actually not very good. And what I'm looking at to determine that is the relative abundance of the various groups. So in black, that is our cyanobacteria. So you see in the summer that it's highly dominated by cyanobacterial species. Okay, so drastically reducing diversity. So that right there tells you something about the water quality. Okay, because you see the reduction in group diversity even. Okay, and here's some of our algae here. Another way that you can look at algae is by using multivariate statistics. So what this is I took a bunch of water samples, looked at species abundance, and I was able to plot the various samples and look at how closely related those samples were. So if samples had very similar species composition and abundances, they would end up being plotted very close together. For example, here, so B is a sample from a backwater, M is a sample from the main channel of the river. So we see that these two samples here, because they fall right next to each other, are very similar in species composition. These two samples, so these were taken the same year, are far apart, so the species composition is very different. When you go back and actually compare that to discharge data, what you realize is the two samples that are close together occurred in a year where there was greater discharge. The two samples that are further apart occurred during a year where there was less discharge. So again, just by looking at the samples, we were able to make some determinations about discharge without even looking at the table for that. Okay. Another thing that I mentioned was the ecology in general, ecology of species. So what this is a paper called Towards a Functional Classification of Freshwater Phytoplankton. And what this does is it breaks down individual species into groups depending on their different sensitivities and tolerances. So that if you identify species, you can then go to this article, an article similar, this has actually been updated by a group, and see what the tolerances and sensitivities are. You can see if this is a species that lives in a more acidic environment. You can see if this is a species that lives in nutrient-poor conditions or nutrient-rich conditions. So just by knowing the ecology, you can then go and figure out what's going on in the water column. Okay. This is an example of diatoms. I already talked about the diatom index. Phytoplankton you can use in larger water bodies such as rivers, lakes, reservoirs. And here's some of the usual suspects that determine poor water quality. And this has been talked about already today, so I think I'll skip past this. So I brought some examples from the Wallkill River. We've had a pretty interesting summer on the Wallkill, and we've had a couple of different blooms of algae. And samples were brought to me, and I looked at them under the microscope, and without even knowing where they were taken, I could determine that the location was either shallow or deep, whether there was some kind of an obstruction to water flow, and also what the nutrient content was. So in this very first bloom here, where the water is more brown, I looked at those species, and based on the species content, I knew that there was high nitrogen and phosphorus. Now, the green, that's Cyanobacteria. When I saw the species there, those species, not only are they known to be very good competitors in nitrogen-poor conditions, but I actually saw the single specialized cells that they use to do that. So I knew that they were actively carrying out nitrogen fixation. So that told me that there was some kind of influx of phosphorus into the water. Okay, the pros of using algae as bioindicators, they're small, they have high growth rates, so they have a very rapid response. Okay, if there's some kind of influx of a nutrient or some kind of change in the environment, the algae are going to be quick to respond to that. So it's as near real time as you're going to get for a biological indicator. Bacteria would be close as well. There's known sensitivities and tolerances, but that does take a little bit of time to find out. Collection and broad species determination is cheap. You can use, cheap microscopes. It's easy to take a sample. And the potential to predict and or form some kind of early detection of water quality changes, the potential is there. The cons is some of these indices require measurements that require expertise. You can simplify that by just training people to look at, this is green algae versus this is cyanobacteria. versus this is diatom. If you wanted to come up with maybe some simpler indices. The species and even genus level can definitely be difficult though. And when you really are looking for species level or even subspecies level, which can be very telling, you need more high-tech microscopes, which can be expensive. Okay, so I just wanted to end with how can citizen scientists use algae? Okay, so in this room, there's a varied amount of people. We have people that have been in the field of science for many, many years, and we have people that may not know anything about science, but have an interest and are involved in citizen science projects. So what citizen science can do is long-term monitoring efforts. Again, this is usually cheap, simple methods. You can simply look at biomass. Is there a lot of algae? Is there not a lot of algae? That tells you that the water is impacted or not impacted. You can look for the presence or absence of the usual suspects. So train people to recognize certain types of cells, cyanobacteria. The see something, say something. If you see something, report it. So it's usually citizens that find these things first. Report, take pictures, go out and take samples if you can. Partner with local schools and colleges. This way, the colleges get the on-site quick response of the citizens, and the citizens get the usefulness of and expertise of the scientists. And training, especially in dealing with nuisance species. So you want to make sure that you're safe in handling these things. Okay, and these are just some sources that you can use. Some of them would be used by people that are used to looking at species, and some of them would be used by this one, for example, just very simple for identifying general groups of algae. Okay, thank you. That's it? Okay, thanks.
All right, thank you. It's very interesting. So it is around 12:20 right now. We're going to break for lunch. Please be back by 1 o'clock sharp, and I mean sharp, because we're going to try to fit in, Al Appleton is now here, so we're going to squeeze him in first. So enjoy your lunch, and thank you to all of our speakers.